using Cramer's rule, find all solutions to the system of linear equations, x plus y equals 3, 2x plus y plus z equals 2, minus y equals 4. But when I use Cramer's rule, my first step is put our system into matrix vector form. So what do? I'm going to peel the coefficients off of x, y, and z of each equation. That's going to give us a row of our matrix. So we'll get 1, 1, 0, 2, 1, 1, and 0, minus 1, 0. Then we'll have column vector of unknowns, column vector of the constant terms from the right-hand side. Now, we're going to use Cramer's rule. What do we need? We're going to take each column of our matrix, we'll call them V1, V2, and V3. We're going to take our matrix, I'm going to take V1, replace it with B. I take the determinant, then I divide by the determinant of the original matrix. That's going to give me a first unknown x. So note, for this to make sense, I have to have the determinant of the original matrix non-zero. So that's also going to guarantee that this matrix has an inverse. But when I get y or z, same procedure. For y, I'll take V2, replace it with B, same idea. For z, I take V3, replace it with B, same idea. To proceed, we need to take the determinant of 4 matrices. The matrices are 3 by 3, so we have options. Let's take a look at the first matrix. So here, no replacement. Now, we have a 1 here in the third column, 0 otherwise, so we might as well use cofactor expansion. In this case, we'll take minus 1 to the row plus column number, so it's going to give me 2, 3, gives me a 5, multiply by the entry, which is a 1, and then we multiply by the determinant of the minor, so that's given by cross out your row and column. Determinant of what's left over is going to be minus 1, so I get a 1 for the determinant of our original matrix. That's good. Cramer's rule applies, and also when I solve for x, y, and z, we're just dividing by 1, so we actually just get our answers when we do the replacements. Now, replacing V1 with B. Okay, so that's going to give us first column 3, 2, 4. No change in procedure. I just target this entry here, so I have minus 1 to the 5th power times a 1 for the entry, and now the minor is going to change. It's just going to be 3, 1, 4, minus 1. Take the determinant, I get a minus 7 times a minus 1 gives me a 7. Next one, replace V2 with B. So we're putting it in the middle column. Again, no change. We're just going to target this entry. So I'll have a minus 1 to the 5, multiply by a 1, then multiply by the determinant of the minor. So that's going to give me a 4 times a minus 1, so I get a minus 4. No surprise there. That's just equation 3. Third replacement. So we have 3, 2, 4 in the third column, and the cofactor trick doesn't work. You could use a cofactor expansion, but you have to deal with 3, 2, 4 instead of a bunch of zeros. So let's just use our diagonal trick. So we go down 3 diagonals to the right multiplying, 3 diagonals to the left subtracting, and then see what comes out. I go down to the right, so I'll have 4. 1 times 2 times 0 gives me 0. 3 times 2 times minus 1 gives me a minus 6. Other direction, so we have 1, 2, minus 1 gives me a minus 2. Since I'm subtracting, it becomes a plus 2. Then I have 1, 2, 4 becomes an 8. Subtract gives me a minus 8. And then for the main diagonal, I get a 3, 1, 0 goes to 0. Collect all the terms, I get a minus 8. Divide by 1, that's my z. Now, our solution is x equals 7, y equals minus 4, z equals minus 8. Of course, we check our work. So I take our x, y, and z, put it back into the original equations, and we note the equations all hold up. So our check works.